charges here add up to the -1 that we have overall. And over here, do all the formal charges add up to +1. Actually, in about half a second, I could have done 0, 0, and 0. Anybody want to know how I know right away those three were 0? Nobody wants to know? Okay, I'll move on. Anytime an atom has its normal numbers of bonds, carbon 4, nitrogen 3 in a lone pair, oxygen 2 and 2 lone pairs, something like fluorine, 1 bond, 3 lone pairs, anything that has its normal numbers of bonds in lone pairs is automatically going to have a formal charge of 0. Backing up, was this a normal oxygen with 2 bonds, 2 lone pairs? Nope, I knew it was going to have a formal charge on it as soon as I looked at it. You see what I'm saying? Because it doesn't have normal bonding, usually that's going to mean a formal charge on it. It doesn't have its normal number of bonds. Does that make a little bit of sense? Does that sound like a useful tip? The hydrogens, they all had the normal number of bonds. So I knew if I did the hydrogens, I'd come up with a formal charge of 0 on all of them. I knew this nitrogen, that's not 3 bonds in a lone pair. I knew that nitrogen was going to have a formal charge. So at this point, you'd probably still have to do the calculation on that nitrogen. Do you think any time you had a nitrogen with 4 bonds and no lone pairs, do you think it'll always work out 3 + 1? Does that seem like it'll always be this equation if it's 4 bonds and no lone pairs? So nitrogen, anytime it's 4 bonds, no lone pairs, which is the second most common bonding after 3 bonds and 1 lone pair. Anytime it's 4 bonds, no lone pair, it'll be a +1. Anytime oxygen is 1 bond, 3 lone pairs, it'll always be -1. It makes some sense. It'll always be the same calculation. So with some practice, you can glance at this and probably within about 3 seconds you're done. And it took everyone 3 seconds this time, right? Does it seem like with a little bit of practice, I might be exaggerating, it might be 5 seconds, but it wouldn't take long at all to do it? Okay, should we go for something more complicated now?
Professor?
Yeah.
I had a question about the NH4.
Yeah.
How that arrangement happens, because nitrogen would have a full valence shell with 3 electrons. So is it acquiring just a proton with the other hydrogen?
In essence, let me just erase a little room. Should ammonium be related to neutral ammonia somehow, NH3? If I take NH3, didn't we just talk about electronegativity? Should this nitrogen possibly be partial negative? If I had an H+ floating nearby, what do you think might happen with that negatively charged nitrogen? Might the H+ want to stick there? By sticking there, that means this pair of electrons reaches out. Remember, an H+ is just a proton, a tiny little speck. Could it probably just stick to the electron cloud pretty easily? And then all of a sudden I have this.
Makes sense. Thank you.
Okay. So just made the same thing. Hopefully that made some sense. I know anything about the hydrogens already? What's the formal charge gonna be on all the hydrogens? 0. Is that like all hydrogens formal charge? Any other one that I already know? Carbon. So carbon formal charge equals what? 0, because it's got 4 single bonds, that's normal for carbon. We did the math before, -4 minus 0 equals 0. Are the oxygens gonna be 0? In fact, are all the oxygens probably gonna have this same exact equation? 6 minus 1 bond minus 6 lone pair electrons. Seem reasonable? Any guesses on the nitrogen? Is that nitrogen with 4 bonds and no lone pairs again? Have we ever seen that before? There's a +1, it would still be a +1 here. So the numbers in the equation would be exactly the same. It would still be 5 minus 4 bonds minus no lone pairs, giving me nitrogen formal charge +1. Doesn't that leave the sulfur? That will actually even take some math. So what group number is sulfur in? 6. So sulfur would normally like to be similar to oxygen, 2 bonds, 2 lone pairs. It's not gonna be here, so that sulfur is gonna have a formal charge. How many bonds does the sulfur have? Got 4 bonds. If I'd had a double bond to something, the double bond would have counted as 2 bonds. Any lone pairs on the sulfur? Yep. So a +2 on the sulfur. Let's see. Since there are there's 4 oxygens. -4 for all the oxygens. +1, +2 more, does that add up to the -1 that it should? Easy, right? And again, it's just looking around and saying, where would the electrons be spread around? The sulfur's a little bit short, there'd be a positive charge there. These oxygens would all have negative charges. For instance, if I had an H plus floating around, would that H plus stick better to the nitrogen in this molecule or to one of the oxygens? What's the charge on nitrogen here? Positive, so would an H plus want to stick to a positive nitrogen? Not really, positives would repel each other, right? What would an H plus want to stick to, what sort of charge? Negative, so we'll probably stick to one of the oxygens. Does it make sense why we would care about what the charges are on atoms in a molecule? Later on, we'll use these sort of ideas to talk about why DNA sticks together as a double strand. Details like that, right, trivia? That's more about electronegativity, but again, both electronegativity and formal charge, that's talking about where are the positives and negatives in the molecule. Okay, so last topic of this chapter is something called bond enthalpy. So with ionic bonds, we had lattice energy. That was pretty much how strong is a bond in an ionic compound. Bond enthalpy is how strong is a covalent bond. has the bond we're interested in. So here we're going to be talking about how strong is the bond between two hydrogen atoms. It has to be measured in the gas phase, so we don't have to worry about interactions with anything else. This way we're only measuring how strong the bond is, not how well it sticks to something else in the liquid phase or something like that. If I hit this with enough energy, can I probably break it into two pieces? I'm just going to measure how much energy it takes to break it apart. So that'll break it up into two hydrogen atoms in the gas phase. All I've done is ripped it right down the middle. And that'll be exothermic or endothermic. I'm going to have to add energy to it to tear it apart. It's going to be a positive number, an endothermic number, and 436 kilojoules per mole of H2. Does this sound like another one of those topics where I'm going to throw a whole bunch of numbers at you? How many think I should make Sam memorize them all? It's going to be, like usual, more about what is the trend than trying to memorize all the numbers I'm throwing at you. And we're going to try to explain the trends. Then, of course, there'll be essay-type questions on the test. Why is this bond stronger than that bond? That sort of thing. Okay, so that was just our first example. Let's throw out several different similar molecules. Hydrogen fluoride, so breaking a hydrogen fluorine bond. Hydrogen chloride, breaking a hydrogen chlorine bond. What do you think would be next? Hydrogen bromide, and after that, hydrogen iodide. Which of these four do you think is strongest? Any guesses? Probably going to be on one end or the other.
Hydrogen fluoride.
Would it be nice if there were some similarity to what happened with lattice energy? What were some of the factors that made for a strong lattice energy?
Radius.
Smaller atoms, that's going to be a factor here. The smaller the atoms, the stronger the bond. So, which has, well, it's hydrogen all the way across, right? So when we talk smaller atoms, we're talking about the halogen. Which of these four halogens is the smallest? Fluorine. So, going to be strongest in that direction. 568 kilojoules per mole. That's one of the strongest single bonds. 431 kilojoules per mole for chlorine. 366. And this one's 298. An average single bond's probably a little bit less than 400 kilojoules. If you wanted a number that represented, quote, an average single bond, a little bit less than 400. Strongest, one of the factors being shorter bond. There's another factor that also makes hydrogen fluoride a stronger bond. Any ideas? Good thing I already erased all the electronegativity stuff over there.
So negativity gets stronger going up and to the right?
Sort of, but we need to continue that thought here. Is there a huge difference in electronegativity between hydrogen and iodine? Probably relatively small. You don't know what iodine is. I know it's 2.5. Hydrogen's 2.1. So isn't that almost nonpolar? What would be just about the most polar covalent bond you could have? The biggest difference between two nonmetals? What's the least electronegative nonmetal you can think of? Any ideas? It would have to be greater than 2.0, right? We said nonmetals were greater than 2.0. What's the next number greater than 2.0? That's hydrogen, right? What's the biggest electronegativity you could have? Fluorine, 4.0. So wouldn't this represent the biggest difference in electronegativity you could have? So stronger bonds are because they're either shorter bonds and or both factors are playing here. The fact that they're shorter bonds and more polar. That's why they're getting stronger. As we go to the left, they're getting more polar and they're getting shorter. I can't really separate out the factors here, both automatically happen. Is that sort of like lattice energy? And then it depends on the size of the charge. That's sort of like our more polar factor and the size of the atoms. It's a lot like lattice energy there. Hopefully this one won't be too difficult. Again, these are just fragments of atoms. These are just fragments of molecules. These aren't the whole molecule. Since carbon has 4 bonds, there's still another bond going off this way, and another one going off that way. We're just looking at a part of the molecule, which you think will be stronger. A single bond, should I say double bond twice as loud? Triple bond 3 times as loud? Which do you think will be stronger? Triple bond. Is that pretty obvious that if it's 3 bonds, it's stronger than 2 bonds, it's stronger than 1 bond? So carbon-carbon single bond on average about 347 kilojoules per mole. What do you think a double bond would be worth then? If a double bond were simply 2 single bonds put together, it'd be close to 700, right? But it's about 620. Is a double bond simply 2 single bonds put together? Or is that significantly less than double? To me, that's significantly less than double. If I just doubled this, I'd get awfully close to 700. It's only 620. What's going to happen next chapter, it'll turn out that this is 1 strong bond and 1 weak bond. And you think that might turn out to be important? The weak bond is going to be something called a pi bond. If I exaggerate the heck out of it, I can say that that's how fission works. Because fission probably is more complicated than is it a double bond or a single bond. In part, the way fission works is because of the presence of this weak pi bond, the weak second bond of a double bond. Triple bond is going to be 1 strong bond, 2 weak bonds. So it's going to go up by an even smaller amount this time. It's 812. But we'll explain more about this idea next chapter. We'll talk about something about sigma and pi bonds. Hopefully you will have corrected this already before I start talking about pi bonds. Let me just squeeze a few more numbers up here. So the trend here was hopefully obvious. More bonds, stronger interaction. Chlorine single bond, 243. Bromine to bromine, 193. Those are kilojoules per mole. What do you think the oxygen-oxygen single bond is going to be? Go ahead and guess. I'll probably only laugh at you if you're wrong.
243.
2335?
Yeah.
No. Well, okay, they might laugh at you too, but. It's actually, different books give slightly different values. I've seen about 150. Our book says 142 kilojoules per mole. Do you notice anything about these three numbers compared to some of the other numbers here? If I just ask you for one word that describes the difference between those top three and sort of the ones I did in the middle, what would it be? Smaller, weaker bonds? Why do you think these three are relatively weak bonds? Would it be nice to know sometimes which bonds are going to be weak as well? You know what made for strong bonds? Polar bonds, short bonds. Shame we don't know what makes for weak bonds. Only there was something that those three had that none of the others had. Yes, I could put lone pairs in here too. Probably be bonds coming out from there. Don't all of these have lone pairs on both atoms? Is that different than what was happening here? In general, if you have lone pairs on both atoms, it's going to make for a pretty weak bond. One possible explanation is maybe they're just repelling each other, giving a pretty weak bond. If you're drawing Lewis dot structures, do you want to intentionally draw really weak bonds? Would that make for an unstable Lewis dot structure? Remember me telling you to try to avoid oxygen-oxygen single bonds because they were weak? So partly I'm just throwing up numbers to support the idea that oxygen-oxygen single bonds are pretty weak. A double bond is a reasonably normal strength double bond, but single bonds are quite weak. You know, hydrogen peroxide is really reactive, right? You know, you just get it starts fizzing, that sort of thing. That's partly because of the weak bond. Do you think I might ask essay questions like, here are some, rank them from strongest to weakest bond? Using these sort of trends? Let's see, what other sort of fun stuff could I come up with, or it might be on the homework?